Well, I think I will be able to make up for some of Roy's lack of PowerPoint. Mine is all PowerPoint. I'd like to thank everyone for inviting me, whoever it was that did it. I made it down. And what I want to talk about, and you sort of got a view of this in the demonstration, is that as we work harder to get information to biological researchers and managers, we end up with a lot of different products, and it starts to get a bit confusing. In fact, I would use the term bewildering array often. And so I just want to talk a bit about the type of data that's available and how does one go about choose what is best for you. I'm sure there's a great range of technical expertise in this audience. And there were a couple of digs at biologists in the last talk. I want to tell you, I love biologists. I particularly like working with them. So one of the things we do is we try to reach out and talk a little bit about that. I want to review just a couple examples of data types. The notion of the artist palette, that is, instead of just using one type, where you have one person in one room looking at, say, SST, and you have another person in another room looking at chlorophyll, another room looking at wind, we try to put them all together. And that, I think, helps synthesize, and one of the things that we've done through Roy's group is make all these available through a uniform interface. And this is fundamental to the idea of distributing them all. I also want to talk about derived products. We spend a lot of time using, say, SST and chlorophyll to compare with animal tracks or habitat models. And I gotta admit, they always seem to pop out to agree the best. I don't think this is a vicarious effect. Now, I'm often reminded that whales don't eat SST. And then I often point out that whales don't eat chlorophyll either, but it's closer to the food chain. So we want to look at things that are more specific to what are relevant to the animals. Now, that includes a number of derived products, as I said. I'm actually not going to cover training opportunities, so we can do that in the session, because there are a number of ways we have of helping people who are not experts in oceanography, or especially satellite oceanography, who can access the data in a meaningful way, such as those methods that Roy showed. And then just some thoughts on the future, where we're going. My goal in my job is to, one, develop the quality descriptions of the marine environment, and two, make these available and easily accessible for a variety of people. My real emphasis as part of the NOAA Coast Watch program is on monitoring, so more of a near real time. However, we're quite aware that that requires historical data to establish the relationships that you will then monitor in your meaningful fashion. Types of data, well, there's of course the in situ, CD and gliders. These were covered very well earlier, so I'm glad I didn't bother spending time on them. Satellite, we have ocean color, which gives us sort of the basic link to biology. Sea surface temperatures, an old workhorse, and it's still used largely because it's by far our longest time series. We're approaching about 30 years now of data, which is getting close to a fisheries type data set. That's always been one of our shortcomings, that we don't have the data depth for proper relationships. I mean, we were talking to Karen Forney earlier today, looking at those 6 precious surveys. And I think there were only like 4,000 data points, which I have breakfast. But each one of those is very valuable. And so we want to make sure we can get the best description of the environment so we don't have to throw those out for our regressions or whatever type of analysis is going on. And that's, again, one of my major, I think, improvements that have been happening over the last couple of years. And then, of course, we have models which give you everything, but it's probably not right. Here's my classic graphic. I stole this from a Navy admiral looking at the CERDIP project for, well, this is a general thing, but they were specifically looking at cetacean avoidance. And just the way it's built up from the basic data sets, the predicted environment, which is more of what a lot of you people do here, the performance evaluation, which is probably something that the customer does, and then the actual application. So I was talking about derived products and how we go beyond very basic geophysical parameters, such as SST and chlorophyll, and talk about the oceanic features that are important to various living marine resources, like generalized here, protected species, fisheries, all that stuff. So ocean fronts and boundaries and edges, we saw some very nice demonstrations of the studies of the fronts today. This is very critical. The mesoscale circulation patterns, again, eddies, meanders, loops, convergence zones where things aggregate, and often aggregation means prey aggregation as well. Get the next one. Winds, ocean surface winds, give you an idea of what's driving the ocean. So it gives you a mechanism of causality. And then wave heights can impact a lot of aspects of, say, fisheries stuff. Maybe not so much in protected species. So I'm going to stick with satellite today. Why use it? Well, you have enhanced spatial coverage. Increasingly good temporal coverage as we get more sensors that measure similar parameters, and then resolves these oceanic features at a variety of scales. And again, we've heard a lot of talk about scales being important to determine how you're going to interpret things. It's also important to what data sets you will choose to use. And ultimately, it doesn't bias the data to wonders near the wealthy nations. So we get to use this and apply our technology across the globe. Now, actually, this is a problematic image to me, because what we've always done in our group, our community, in satellite stuff, is oversell our ability to provide products. So we have a picture off the coast of Oregon here. SST is on your left, chlorophyll on your right. Now, it looks like this about once a decade. This happens to be September 28th, I think, 1998. And I know them all. There are about 5 of them. And people see this and say, wow, we can do everything with this. But you can't. Here's an example of a more typical image. Now again, this is the coast of Oregon. I wanted to exaggerate because the remote sensing is terrible there. In the Southern California bight, it's actually quite good. You get about 100 good days a year. So you can really work with that. But just an idea of why we need to be realistic in our expectations and in our projections. And again, the problem that we had talked about today, you generally only see the very surface of the ocean, or at the very best, some integrated upper layer. We have to account for a lot of factors in measurement, many of which we can't directly determine. This largely has to do with atmospheric corrections, orbit errors in the spacecraft, that sort of thing. Stuff that you should never have to worry about, I hope. That's our job. And we can only derive a very basic set of oceanographic parameters. And of course, clouds are an issue for all visible and infrared measurements. They just do not penetrate. So an example of how we get around this is, one, we've learned enough about the error measurements, the characteristics of the various sensors, that we can actually combine them in a sensible manner. So here's an example. I've taken 4 different spacecraft. This is sea surface temperature. One from the MODIS sensor, which is a NASA sensor, one from AHR sensor, which is NOAA, one from GOES, which is also NOAA, and one from AMSRE, which is Japanese. The first 3 are all infrared measurements. And again, these are, in a sense, independent. In a sense, not because obviously they're measuring the same environment. But they all make the measurements by themselves. And then I've also included the microwave measurement. It sees through clouds, but the problem is it doesn't work near land, because the land contaminates the signal. But you can see that the infrared does work pretty well near land. But if I put them all together, I get this. Now, a lot of managers that I approach often get on my case about having holes in the data set. They can't tolerate it. In fact, a lot of the regression analyses that you use, GAMs, things like that, abhor gaps. And of course, as I mentioned, you want to have a good distribution environment everywhere. So there's a program called the Group for High Resolution SST. It's international, and they have standardized formats with all the stuff that we like to have under our hood. So I can just take their files and slide them right in. Nobody even notices. The provision of error fields allows users to better understand the data set. It also allows us to do a better job of combining the various sensors. And again, the documentation is superb. Another great example in the terms of satellite work was the reduction of the error in altimeters that measure the height of the ocean surface. Okay. Logarithmic scale, so you can see it's really improved since 1978. To the point now we have Jason 1 and now we have Jason 2. It's down to about 1 centimeter through precise orbit calculation. And again, understanding all the errors in that measurement, and there's a lot of them in terms of atmospheric interference and things like that. So just the idea is that we're enabling our other people to understand what we need to do to make a better product that's suited. And one question I can throw out to you, and you can take your time getting back to me on this because it's a complex question. What about your error budgets? What is your tolerance for error in our products? If we know that, we can be more efficient in targeting. Obviously, the spatial and temporal requirements are very important. Again, that's a function of scale, both in space and time. And what are we actually trying to measure? It probably isn't just SST or chlorophyll. It might be one of those other parameters that maybe we can do something about. For instance, one frontal product we make is from a geostationary satellite. So it takes an image every hour. And so instead of worrying about the clouds being in the way, just wait for them to move. You make a composite image, then you can derive these frontal products. Just a couple examples. Things that are a little more highly derived. This is from altimetry. It's called eddy kinetic energy, which gives you an idea of the mesoscale variety. Now you see a streak along the elutions because this is a quarterly average. And it shows the eddies moving along those elutions. And then why parameterize? You can actually detect the things. Here's a map, just a snapshot, a 10-day snapshot of all the eddies off the coast of California. We can identify them and track them. In fact, once you track them, you can look inside the chlorophyll and see what's changing with biology. We're a little far away from doing that yet, but that's coming down the pipe. The near future, models for hindcasting. That's already going on now. Soon, models for nowcasting. That's also going on now. And then models for forecasting. These models will assimilate data to make them better models. And again, we have a pretty good observing system. They're getting good enough to look at seriously, as you might have seen in Karen Horney's talk earlier this morning. So we are taking this seriously, and it's just a matter of time, I think, before they get good enough to use. You're not going to be saying what's happening on September 27th at 10 o'clock, but you will be able to say easily what was sort of generally the situation in September. And that's sort of the realistic expectation, I think, for that process. So anyway, I think we'll have these posted somewhere, so should you want to contact me, this will be the place. Or just call Daniel or any of us. Thank you.